Welcome back, guys. It's great to be back and have the opportunity to explain once more the support vector machine problem. We're going to call this problem as the primal problem, the first problem we found together. Okay? So on top of this primal problem, in this class, in this video, we are going to build up what is called, what is referred to as the dual problem. We'll take advantage of the Lagrange multipliers and the Karush-Tucker multipliers that we discussed in the previous video. Okay, so basically, let's go back. We found this problem. This is the problem we found exactly in the previous video. We've got a minimization problem to be solved in which we can adapt W. W is a vector, and I'm just writing that this vector belongs to a Hilbert space. This is the same as, just to have like a basic idea, this is the same as saying our problem belongs to a complete metric space. Or if you prefer, just imagine like R2 or R3, R4. Of course, that dimensionality is related to the input space dimension. So if my input space dimension is like, we've got like 5 dimensions, our vector W will also have 5 dimensions, okay? And then we have a scalar number belonging to the real line. This is the intersection point that's going to define how our hyperplane is going to cut the space. It's going to divide positive from the negative side. Okay. Here I just decided to call this as tau or something, but actually this is not important. Important is this term over here. So I need to minimize the norm to the square, the norm of this vector W. I think you probably remember the previous video. I told you guys that this half was part of our formulation, but this this square that appears over here is just to help us solving this problem, just like an adaptation for convenience to make it easier to solve. In this video, you're going to see that this makes a huge difference in simplifying our solution, simplifying the way we solve our problem. This is subject to, so those are the constraints again. Of course, when I perform the dot product in between my vector W and a given point in my space, a point that could belong to the positive or the negative class, plus some B, this multiplied by the class, either positive, either +1, okay, positive, or -1, negative, should be greater than or equal to 1, okay? This basically means if you guys don't want to see this yi over here, you can just pass it to the other side and you can imagine, okay, I have to be greater than or equal to a given number that's on the other side. Of course, if it's positive, greater than or equal to +1. If it's negative, it should be smaller than or equal, okay, to -1 over here. So all the foundation I gave you guys in the previous videos on Lagrange multipliers and Karush-Tucker conditions, and of course multipliers, are necessary to solve this optimization problem. You know what's interesting? We now take advantage of a way of reformulating our problem. We can use Lagrange multipliers and Karush-Tucker multipliers to reformulate this problem in a different space. This is in a given space in which we have to actually minimize in terms of W and B subject to those constraints. What happens if I try to write this problem in a different way? I can find what is called the dual problem. So you can see this as our first problem form, or the first way we formulate our problem. If I come up with a second formulation that produces the same result, that is my dual form. Okay, so we've got two forms for every optimization problem we have. We can write it in two different forms. That's so way interesting, because maybe the second form turns out to be easier to be solved. So that's something I'm going to discuss in this video. Okay, so going further, we've got the Lagrange-Tucker conditions that must be satisfied. Why? Because our constraints are inequality constraints. Okay, so I need to satisfy the Lagrange-Tucker conditions. The first one is I need to satisfy all primal constraints. What is satisfying all primal constraints? It is satisfying those constraints over here for every point I have in my space, considering I have a sample size with m points over here, okay? That's something, at this point, we are going to assume, we're going to suppose, then we're going to confirm when solving for a particular problem, of course. The second one is the stationarity condition. I suppose you guys remember, I wrote a Lagrangian function, lambda, in the previous video. In that lambda, I just wrote here the variables we are going to differentiate into. So we've got the vector w, b, which is a scalar value, and some Lagrange-Tucker multiplier alpha. This is our Lagrangian function. It is basically our optimization function, okay? Half times the norm of w to the square minus some alpha multiplied by each of those constraints we've got. Those constraints have to be equal to 0. That's why this is -1 over here. I just brought this one to this side and solved for the equality as discussed before. At this point, I'm not going into the details for Lagrange-Tucker and Lagrange. In the previous videos, I discussed just the necessary, just basics to bring you guys to this video and just tell you, like, okay, we've got Lagrange multipliers and Lagrange-Tucker conditions / multipliers as a way of solving or rewriting this problem, this primal problem, into its dual form. Okay, so all those Lagrange-Tucker multipliers, of course, if we've got like m points in my space, we've got m constraints, and we've got m Lagrange-Tucker multipliers. Probably remember, I didn't provide you guys all theoretical foundation on that we are going to discuss, but this sign has to be negative because I'm building up a minimization form. I'm coming from a minimization form, okay? That's okay for now. It doesn't matter if you guys don't know that into the details. Next classes will be on optimization. So we're going to have an opportunity to discuss all that. You know, even if you don't know it, or if you know it, you're going to remember it, okay? Third Lagrange-Tucker condition is called complementary slackness. That is basically, that tells me that every Lagrange-Tucker multiplier times the inequality constraint, times its, of course, inequality constraint, had to provide a sum equals to 0. Okay, that's a necessary constraint Lagrange-Tucker condition. Otherwise, we don't have a solution. That's interesting. It is interesting to mention that many of those constraints will be non-binding. You know what's interesting to tell you at this point? The closest point or points to the hyperplane, in this case, we've got this green point, let's say it belongs to the positive class. It is the closest to the hyperplane. This red point, it is the closest from the negative side, from the negative class to the hyperplane. What's going to happen? Those 2 points will be support points, or they will define the support hyperplanes as sidewalks, as we've discussed before. Those points, 2 red points over here, which are far from the hyperplane, and the green points, which are also far enough, at least, from the hyperplane, they will have Cauchy-Tucker multipliers equal to 0. So there is something quite interesting here to mention. This guy over here is going to define a constraint that is necessary for my problem, that is binding. Those over here will define non-binding constraints, because if this one is satisfied, these others constraints over here will be, of course, satisfied, because I will have a constraint in terms of this point and a constraint in terms of this point. How can I be sure that I will have those constraints? Remember, for each point, dot product by my vector plus b, I have to satisfy this constraint. Take a look. It is a constraint in terms of some point that must be positive or negative. Of course, if I satisfy for this closest point, I will be satisfying for those 2. If I satisfy the constraint for this point, I will be satisfying for these 2 points just by definition, because this one is closer to the hyperplane and this one is closer. So something quite interesting appears at this point. The closest points will have alpha, that Cauchy-Tucker multiplier greater than 0. Those others over here and over here will have an associated alpha or Cauchy-Tucker multiplier equals, of course, to 0. You know what's nice? Just remember, every point of Goldman space will have a given constraint associated to it. Something quite interesting to mention at this point. If you guys come up with an optimization that the number of points selected to derive somehow or to induce somehow the sidewalks, or as we mentioned before, the support hyperplanes, one over here for the positive class, one over there for the negative class. If you've got few points defining the support hyperplanes, that means your solution is better than if you need more points to define a sidewalk here and another here. Why that? Because of course you have less complexity in terms of the constraints to solve your problem. You need to deal with less constraints instead of more constraints. Okay, just to have that in mind, just to bring some interesting concept to you. Okay, so going to the next, the fourth and last Cauchy-Tucker condition we must satisfy is the dual feasibility. The dual feasibility tells us that every alpha or Cauchy-Tucker multiplier has to be greater than or equal to 0. Of course, we don't accept negative values. It has to be semi-positive. That's the name for this, semi-positive. Okay, it has to be a semi-positive. Each value has to be semi-positive. It has to be greater than or equal to 0. That was given before. Again, I didn't prove that for you guys. I didn't show you the details on that. We are going to discuss that later. You know why? Because I'm just assuming, okay, guys, we have to find the optimization, the prime optimization problem for the support vector machine, which is based on the large margin bound, which just tells us, okay, if we follow that bound, we are finding the best solution, the best classification solution or classification algorithm for any particular scenario. Of course, provided our input space is linearly separable. Of course, if I don't have a linear separable problem, I need to apply a kernel in my space to transform it to a different space so I can come up with a linear separable boundary or hyperplane, so to speak. Okay? Going into the details, now we are going to use Lagrange multipliers, and of course, that's the same as using the Cauchy-Tucker multipliers if you consider the second Cauchy-Tucker condition, which is stationarity. We're going to take advantage of that Lagrangian lambda to find the dual problem. Now you guys will have this subject on how to come up with a primal problem, a first problem, and find a second way of representing the same problem. What is interesting about this is maybe my first problem is easier to solve, maybe my second problem is easier to solve. Sometimes both problems need to, they can help and they can be kind of plugged together so we can take advantage of both to solve our final problem. That's the same as saying that I can solve both problems together to find a best solution. Okay? Sometimes using the first, sometimes using the second, sometimes using both together. So this is our Lagrangian. Remember, lambda, our vector, our scalar value, and a vector, this is a vector, okay? Including all all Cauchy-Tucker multipliers, all Cauchy-Tucker multipliers. And this is our Lagrangian. Again, negative because this is a minimization problem. How can I find the dual problem based on this primal problem whose Lagrangian is in here? I have to differentiate in terms of W, B, and alpha. When I differentiate in terms of W, I have something. In terms of B, I have something. In terms of alpha, I've got the constraints because all constraints are multiplied by alphas. Okay? So differentiating lambda in terms of W, what I'm going to have, and this is why we used this square over here. We're going to have this square is going to come down and it's going to be divided by 2. So we're going to have 1 times W or the norm of W, okay? So this is so way interesting. This is so way interesting. That's why we've got this W over here, okay? This was just by convenience to make it easier to solve the differentiation. And now we've got this, from this side, we've got W times, of course, there is an inner product here, so we still have Xi, and that's going to be multiplied by Yi and by alpha I. That's why we've got alpha I, Yi, Xi from 1 to n. And this is going to be equal to 0. Again, why this? To have parallel gradient vectors. This is the same as making W equals to this guy bringing to the other side, just to make sure we're going to have a parallel vectors in terms of our optimization function and of course our constraints at this point in terms of W, but we still have to differentiate in terms of the others. So we've got this as a partial solution for W. Okay, just remember this. W will be equal to this, okay? We're going to substitute this W here. That substitution is going to help us to find the dual problem from this first or primal problem, okay? That's quite important. We're going to use that later. Now we differentiate lambda in terms of B. This is going to be 0, and this is going to be, wow, B is going to be multiplied by Y, I, by alpha I. So it's going to be alpha and Y, of course, one multiplied by the other, given this sum, and of course, this minus sign. Minus sign is going to be the sum of alphas and times y's, okay? And that equals to 0. Again, y equals to 0. This is to ensure basically the parallel vectors again, okay? The parallel gradient vectors, sorry. So again, what's nice now? We can proceed with substitutions. Every time a substitution cancels out a term, just keep that in mind. That particular substitution should be aggregated as a constraint for our dual problem. That's the case at this point. Why that's the case? Just getting back, just gonna go back here. If I open up this term, what I'm going to have, you guys can take a look here, and if I multiply alphas, y's, and this inner product, I will have this, alphas, y's, and the inner product. Kind of easy, right? In terms of b, I will have b times y's times alphas. So I have this, b times times, of course, the sum of alphas times y's, okay? And it's going to be a negative sign over here just because this is a negative sign, okay? So this term comes from that decomposition. Of course, we've got still to distribute this 1 over here. So minus 1, and this is a negative. Of course, it's going to be positive alphas times y's. So positive alphas times y's. Oops. Oh, sorry. Just 1 times alphas, because y is just times those inner terms over here. So it's going to be just like minus 1 times alpha and a negative sign. It's going to be a sum of alphas. That's okay. On top of this, that's basically the same formulation, but we're just distributing the terms over here. What is interesting about that is, from the previous derivative we found, or differentiation we made of our Lagrangian function lambda in terms of b, we found this. This has to be equals to 0. What is interesting, I can just come up here and substitute this. Making this equals to 0, I have this as a partial solution at this point. Again, just remember, whenever a term is substituted on my original Lagrangian function and something just vanished, I need to add this as a constraint in my dual problem. That's for later, but okay, it's good to remember. Next step, this is my problem at this point. What did I learn after differentiating my Lagrangian function lambda in terms of w? I've got this as one of the solutions. When I have this, I can perform substitutions in terms of w. What is the norm to the square? That's a square root of a dot product powered by 2. Okay? So, of course, if it's a square root and on top I have a power of 2, I can just cancel out my square root and I will have the inner product over here, just the inner product. This is w, take a look. This is w, just a substitution. W and w again. That's my w with half over here because I canceled out my square root with this power of 2. So of course I have this dot product inside. Here I have minus sum of something, and here I have again w. I can substitute this w, and this is the substitution. Take a look, okay? Plus a sum of alphas, as shown in here. What is interesting about the dot product is that it is a linear transformation. So as it is a linear transformation, I can take advantage of this scalar multiplication, because this is a scalar number, this is also, and this is a sum. I can just bring that outside of my inner product because of the linear transformation condition or principle, if you prefer. This happens the same here and happens the same over here. So what's interesting is this. I can just bring these sums, all these sums outside. So this will be a sum in terms of I and this in terms of j. You guys can see here, okay? And I will have alpha I, alpha j, y I, y j, and the dot product or inner product of xi, xj inside. Take a look. It is inside. Okay? All inside. Of course, with this sum, I can do the same. I can perform the same task. I can bring this outside. And it will be the sum in terms of I, in terms of j, two sums. And we have alpha I, alpha j, y I, y j. And inside our dot product, xi, xj. What is amazing about this? And of course, the sum of alphas I. What is amazing about this is this term is the same as this term, but it's a half of this term over here. Take a look. Just compare. Compare all elements. This is half of this, and this is negative, while this is positive. So I can simplify this. How could I simplify? I could just perform this subtraction, and I will have minus half of this sum, minus half of this sum, plus alpha, plus the sum of alpha I. This is a very nice simplification. Take a look. Y's are given, they were at least given at the beginning because we had the training set, and we need to ensure the solution for our training set. Those are the points we've got for our training set. Instead of having W and B, now we just have our solution in terms of alphas. What is interesting is, instead of finding our solution for W and for B, which have different scales and belong to different spaces, one belongs to the Hilbert space, W, of course, and the other belongs to a real line. So they've got different scales eventually. Here we've got alphas and they've got the same scales. They just have to be greater than or equal to 0. It becomes simple to solve this problem. Take a look. This can be rewritten, of course. This is actually already our dual problem. The dual form, or the second way of representing our first, aka primal problem. Of course, we've got like some conditions to be satisfied. First of all, our alphas I have to be greater than or equal to 0 for all points in our space, all m points in our space. There is something else. We can simplify that. Instead of writing our Lagrangian like this, we can write our Lagrangian as, I just call it W. Could be any letter over here. Uppercase, of course, to differentiate from like lowercase, which is our vector of alpha. This is going to be our Lagrangian function for the dual problem. Why here we've got W, B, and alpha? Because those are our variables to be adapted. But now, after substituting all those W's and B's over here, we've got just alpha to be found. So we have a simple problem. We just need to find alpha. Instead of finding 3 different variables in our primal problem, in our second or dual problem, we only have alphas to be found, okay? Or estimated, if you prefer, or optimized, if you prefer. This is our formulation at this point for our dual problem, or second way of representing the same problem we had at the beginning, okay? What is interesting now is we still need to adapt and add up another constraint in our dual form, in our dual problem. Remember, this was a differentiation result found from the primal problem, but after the substitution, it was vanished in our Lagrangian. Whenever a term is vanished in our Lagrangian, I told you guys we have to add it as a constraint in our problem. It could be a constraint using this negative sign, but actually I prefer to multiply both sides by -1 and make this positive. So it's going to be a sum, a positive sum equals 0. Anyway, multiplying by -1, all this equation is going to be the same without the sign, okay? So this is our problem to be solved now in its dual form. Whenever we go for a dual form, we need to pay attention on something. If the primal problem was a minimization problem, the dual is going to be the opposite. It's going to be a maximization. If the primal problem was a maximization problem, the dual will be a minimization. It's always the opposite, okay? That's quite interesting because I can use the Lagrange and Cauchy-Tucker conditions on top of this once more and find the primal problem again. That's something I just leave you as homework. Please try to take this problem as if it were your primal and try to find the dual, which is going to be the primal that we discussed at the beginning of this class. So this is our dual problem at this point. What can I solve? I can solve this problem or the first or the primal. It doesn't matter. Both are going to provide the same solution. What is interesting? Just imagine this. Just imagine this. I want you to close your eyes and think. In the primal problem, I had a minimization problem in terms of W, B, and alphas. So my space had like a bunch of x's. One of the x's was like W, first value of that vector W, second value of the vector W, third value of the vector W, and so on. A vector representing a single B, and of course all the other x's, one for each point you had in your space representing a given alpha. Alpha 1, alpha 2, alpha 3, alpha 4, alpha, and so on. Okay? In this case, your space is just simple. You don't have like those x's for w's. You don't have those x's for p's. You only have x's for alphas. So it's going to be a simple problem. And that's really interesting. Okay, so those are the differences between primal and dual in this case. Just again, at this point, we need to remember that we need to provide some solution. Whenever our point lies exactly on the hyperplane, the result is going to be 0. So if it lies on the hyperplane, our dot product of vector W by vector xi, which represents a point in our sample, plus some b is going to be 0. Whenever a point is on the positive side, let's say it's this side, is going to be greater than 0. And whenever a point is on the other side, the negative side is going to be smaller than 0. Just remember, okay? So this is the way we finally formulate our solution. This is our dual problem, again, just shown here. And to find our hyperplane, we are going to have, again, a sine function. A function that provides a sign if it's positive or negative, just telling us if we are on one side or the other side of the hyperplane, and of course could be 0 if the example lies exactly on the hyperplane. We've got W, and we know how to find W, right? Actually W is exactly this, okay? And we've got X, which is a given point we need to classify, and some B. W was found before, and here I just produced a substitution of W to find this formulation. Of course, this is the way of formulating our problem. We just need to find B. This is the function at the end. After optimizing our dual problem, we are going to apply the same function we used in the primal form. However, B has to be found What is the solution for B? I think you guys remember that the differentiation, if you differentiate lambda in terms of alpha, we've got what? We've got the constraints. So we can use the constraints to form this B. Again, if we differentiate, we're going to have a constraint for the closest positive point. The closest has to be positive 1. And the closest negative point, or negative points, if we've got like several points, have to be or has to be minus 1. If we sum up those two, take a look, the sum of those two conditions or constraints will provide the result. By summing up, I have this plus this, take a look, and 2 times b. Okay, and of course here is going to be 0, because of plus 1 and minus 1 will be 0. So if I solve this for b, I have minus half b times this product. What is the solution for this guy? I just have to have the closest positive point, the closest negative point to the hyperplane. And that's going to be my solution for this b. Oh, that's quite nice. Okay, now I'm just gonna give you guys an example. Just imagine I have a quite simple scenario, just 2 points, one positive, one negative. Let's suppose the positive point is exactly on the position 1, 1 in my bidimensional space, input space, and my negative point, minus 1, is at the point, the coordinate, minus 1, minus 1. It is in here, okay? So my hyperplane will cut my space somehow over here. That's good. Try to test our Lagrangian for both alphas, for the alpha of this guy and the alpha of this guy. Just assume alpha of this point being equal to 0.1, and this one 0.1 as well. Then 0.3 here, 0.3 here. Then 0.5, then 0.7, 1, 5, 10, 10. And solve the Lagrangian for that. Just as an example. You know what? Here is the dual problem. Let's test it. Here is a code, a quite simple code you guys can copy, or maybe just use my implementation, because here I'm going to create example 5. In example 5, we'll basically type this code over here. Okay, oh yeah, maybe I can copy it, explain the code for you, and make some adaptations. I think that will be quite interesting. This is our support vector machine solution using its dual form. Okay, but of course it's not yet the optimization, the real optimization for a real world problem. This is just like a toy, a very basic toy. Here I'm defining, as you guys can see, this is going to be my input space. Input space. This is a positive point in a bidimensional space. Positive point, and this is a negative point, or negative example, if you guys prefer. Okay? Point or example, if you prefer. Of course, here I'm defining the output space, or labels, or class labels. So I've got one positive example and one negative example in the same order of this matrix X. So here I've got like the first element is positive, the second negative, and the same order here, the first positive, the second negative. This is the definition of a vector. If you guys don't know R, this is a definition of a vector C. Here I'm just guessing some alpha values just to test, okay? And here we are computing the dual optimization function. So what is our optimization function W of alphas? That will be a 4 for every I and for every j, as you might see over here in our formulation, i's and j's, okay? And inside I will multiply alphas, I, j, yi, yj, and this inner product, if you prefer. So of course, w of alpha, sorry, will be equal to itself plus something. Plus what? Alpha I times alpha j times yi times yj times something else, which is my inner product. So my dot product xi, xj, it is in here, okay? After computing all that, I just need to do what? I just need to multiply this by minus half, because this is my partial solution, plus the sum of alphas, which is in here, the sum of alphas, okay? And this is going to be my result. Of course, I'm going to print the result for you. There is an issue over here. What is the issue? My basic issue is, of course, my issues are resultant of my constraints, but let's see that later. I'm going to improve this for you. So this is the result of my optimization function. So let's print like this. So our W of alpha, or alphas, because we got like a bunch. Okay, it's a vector, of course. Yes, this, exactly this. Let's print it. Let's see the result. I'm going to open another terminal and then R and then load my code. What's the name? Oh yeah, SVM duo. That's my result, 0.16. What happens if maybe I try different values? I could try like 0.5, 0.5. Let's see the result. Ooh, no, it's smaller. I want to maximize, so it's not a good solution. Maybe 0.4. Maybe 0.4. Let's see the result. Oh, 16. 0.16. Oh, that's good. It's increasing again. Maybe 0.3. Let's see what happens. Wow, that's even better because I want to maximize. Yeah, let's see, maybe 0.2. Let's see what happens if I, instead of 0.1, I try 0.2. 24 again. What happens if I try like 0.25? 0.25, let's see. Wow, that's even better. Whoa, that's good. You know what's nice? We could try different values for alpha. What if we come up with something like this? Let's call this as value, and value will be in a sequence. I'm going to use the same value. Of course, my alphas have to be greater than or equal to 0. So I will start with 0, no problem, and I go up to 1. And I will create a sequence with 100 values over here. And for each value, I will perform this very same operation over here. You know what's interesting? I'm going to do something like this. So instead of defining guess alpha like that, just set value and value. I'm going to use the same value for alpha, okay? And we have a solution here. You know what's interesting? I could just create a matrix and save up into that matrix the value that I used for both alphas. Of course, they could be different, but at this point, I'm going to use the same value and the result that I want to maximize. And this will be a matrix starting with some new value. You know what's nice? We could, at this point, plot R to see which point maximizes our optimization function. So let's load it. Wow, so nice, guys, so interesting. Take a look. Take a look. Maybe you could even plot like with PCH and 20 and maybe CX3, that's going to give us like a solution like that. Oh, even better. Take a look. The perfect solution is actually 0.25, which is in here, twice in here. Oh, that's so interesting. How could I know that? Of course, I could just ask for this matrix R, which is the greatest result, which is in the second column, which is the maximal value. And it is going to result in some ID. And I can just print, okay, R in that particular row brings the best result found. Let's run it. Oh yeah, it's not 0.25 exactly because our sequence is not passing along 0.25. Of course, if I somehow increase my sequence here to 150 values, I will get closer to 0.25. If I increase even more, let's try like this. I'm going to be even closer, maybe, yeah. Of course, I could have like 500 points in my sequence, and it would be very, very close. That's enough. Let's say that's enough. Or maybe, I don't know, maybe I could use like 1000 and try to get like really close, even closer. Maybe, yeah, you know what? The problem here, of course, is that I'm not at that exact point. But no problem. Let's use this as our solution. What can I do with this as my solution? I can test the constraints. First of all, my alphas are greater than or equal to 0. Yeah, of course, that's a value. Now, what happens if I multiply this by its corresponding class? Where are the classes? The classes are here, -1 and +1. What should I do? I should create a vector with my alphas like this and multiply both by my vector y and sum up. That's the same as an inner product or dot product again. Take a look. The result is 0. Did I solve my problem? Yeah, because I maximized this and I am respecting my constraints. First of all, alpha 1 has to be greater than or equal to 0. 2 also. Okay, that's satisfied over here. Second, my dot product in between alphas and y's has to be equals 0. It is? Yeah, it is. That's perfect. Yeah, that's our first solution. Going back to our slides, just try with different alphas as I did here, please guys. And now, of course, we can come up with our solution. If we prefer, we can solve this. Of course, it's nice to solve this. What's going to be my sine function? It's going to be like this. A sine function in terms of my inner product of w dot product sum x, you guys define, plus b. How can I compute w? Do you guys remember? How can I compute w? If I go back, go back, what is the solution for that? Take a look. We have that by differentiating. Wow, that's the solution for w. So w is the same of what? Alphas, of course, multiplied by y's, multiplied by what? By all values of x. So if I come up here, it's alphas over here. Take a look. That will be times y's. So, okay, it's in here. Of course, alphas. Oh, yeah, alphas here are like 1, 1. Sorry, our correct alpha is here. R of ID. Some ID, sorry. Yeah. times y, it's going to be this, okay, times something else, times what? Oh, sorry, it's the first element. Sorry, guys. The first element is the value of alpha. Yeah, I need to repeat it once more. So we'll have the same value for alpha for both points in my space. Oh yeah, no, it's okay. So times y, that's okay. And that times what? X. Is that right? Is that right? What is x? You guys remember? Okay, that's my first value. So it's going to be this vector. This first vector actually should be like this. The first vector times this, and then the second vector times this. Yeah, it should be like this. So it should be exactly this. Let's copy. Let's bring it here. So it will be this. This is going to be my W. W is going to be alpha 1, alpha 2 times y times my first vector. Of course, I have to vary my vectors here, so I will vary from 1 to the number of vectors I have in X, in my input space. And of course, my first value for W will be 0, 0, and then I have to sum up. As you guys might see here, it is a sum in terms of n, in terms of the number of points I've got in my input space. That's the same as doing this. W equals, or receive W plus this computation. Of course, we have W now, but we don't have B yet. What is going to value for B? B is going to be minus half, sorry, I suppose you guys remember, minus half times of what? Some inner product. You probably remember, it is over here. Where is it? Just don't remember. It's around here. It's around here. Yeah, over here. Yeah. So I've got the positive point. What is the positive point at this point? It is x at the first row. Of course, plus x at the second row, like this, and that inner product, dot product by W, all that multiplied by minus half. That's my B. Wow, so nice. Oh, good. So here I could bring up any point in my space, let's call this as a test x to be tested. And here I will be its result. Okay, so what's going to happen? Now I want to give you an idea. Let's come up with two loops. And this first loop will vary, of course, my first value of x. This could be like, let's call this as my first dimension, or my first attribute, could be like this. First attribute, varying in a given range. I could go like from -5 to +5 and divide this interval like in 100 possible values, and here could be the same for attribute 2. Attribute 1 and attribute 2 together will provide my x test, and then I apply. Of course, you'll have a result for that. What is interesting here is I could plot that. I could save up that in some matrix M. That matrix could contain something like this along the rows. That's why row bind could contain something like, okay, it's going to contain x test, and it's going to contain y test. Let's see if this runs. I'm not sure if this is going to run or not. Let's see what is in M. Oh yeah, it's there. There is something here in M, but it looks like the results are wrong. I don't know, probably. Yeah, let's see what's happening here. First of all, let's see my W. Oh, W is 0, 0. Why 0, 0? Isn't it like, what is happening here? Is it running here? This guy over here? Let's see the number of rows of my matrix X, 2, okay? So I will come up with this solution. So my W over here will be, of course, R ID 1 and R of ID 1 again. Those are my alphas. Okay, perfect. Times Y, perfect. Times what? Times my first element. And when I do the same for my second, take a look. This will cancel out with this, and this will cancel out with this. That's why W is 0, 0. Okay, that makes sense. What's going to happen with my B? Oh, it's 0 again. Let's see. Okay, X1 and X2. What is the result of X1? 1, 1. And X2, minus 1, minus 1. What happens if I multiply, if I sum up both? Okay, it's going to be this plus this, 0. This plus this, 0. Okay, so it's going to be a vector of 0, 0. That's okay for now. And then I compute the dot product, or the inner product by W, and that's going to be B equals 0. Okay, that's going to be B equals 0. It makes sense again. Okay, so what's going to happen with my sine function, this sine function over here? Oh, let's see. Let's see what happens with W and B. Of course, if I take my first point, what is my first point? It is X1, which is positive, applied by inner product by W. Okay, it's going to be 0. And I sum up with some B. Oh, it's going to be 0 again. Oof, what's happening here? Take a look. I need to come up with some positive, either negative results. Something's happening here. There is like some issue with my code. What is the issue? I don't know what's happening. Maybe, and just maybe, I could change something. I could come up with a different solution. The question that I leave for you guys to assess, to think, is why I've got this particular solution. Is there something wrong with my code? Just send messages in this video, in the comments of this video. Okay, I'm just going to give you like some additional information here. So this is for plotting our best solution. Solution found for alpha, actually for alphas. This is, in here we are finding or getting maybe the best alpha value found. Okay, here we are printing alpha, the alpha value, to be more precise, the alpha value, and of course the maximization of our optimization function, or objective function if you prefer, objective function, or our goal. Here we are computing W. Here we are computing B. Okay, computing some B. Okay, and then here, that's okay, that's all right over here. Just try to imagine something. Let's consider that instead of B being like perfect, like +1, this could be like 1.0001. This could be like, instead of -1, this could be like 0.999. This could be like 0.999. It's almost like +1, -1, -1. Just consider this What's going to happen with my results now? Take a look. I've got some perturbation now. I want you to plot this M. I'm going to plot for you M in terms of the first and second columns and the color. Well, actually not the color. Let's plot, just for now, let's plot the points. And of course I have an issue with the colors because some of the colors, if you guys look here, will be -1. I cannot plot something that is -1. I cannot plot something that's 0. So I need to make this at least equal to 1. So I need to sum up 2. So if I sum up 2, I'll have at least 1 for the negative side, 2 when some point lies on the hyperplane, and 3 for positive. Let's plot like this. And you guys just imagine what's happening here. Take a look. Hyperplane, positives and negatives. Okay? What is happening here, guys? What is happening in my space? +1, +1, minus, almost -1, -1. Just imagine, this is the hyperplane. Think about what is happening over here. I'm going to copy for you. Of course, I will plot it for you over here. So plotting. What happens when I don't have like this small perturbation? But instead of having this small perturbation, I have something like this. What is happening if I've got like +1 and -1? Just want you guys to verify. Without that small perturbation, I've just found W and B both equal to 0. Instead of being like +1, +1, and -1, -1, what would happen? This is like plus also, and this is also plus something in a different place of my space, like +5 and +5. Just imagine this. Would I have the solution? I'm going to run for you. Oh yeah, I found it. Oh, it's interesting. Why? When I have this case, guys, when one point on the positive class is exactly on the same point, the closest of the negative class, they cancel out each other. So I need like some sort of small perturbation to bring the result. For this particular algorithm, we implemented, because it's not a good solution, just an approximation. It's a very simple approximation. Now I want you guys to come up with another SVM implementation by you. So you guys implement either the primal or the dual form and find some solution for your problem, for this support vector machine problem. Again, just remember, support vector machines provide the best classification algorithm ever if and only if my space, my input space, is linearly separable. If I can divide my space into half spaces, having negative elements on one side and positives on the other. If I don't have that, I need to come up with kernels, with some kernel. And the kernel is going to, I expect at least, is going to allow such linear separability. It should, at least. See you guys.